So Fei is a professor at USC, so not far from me. And again, this is part of the Rising Star sequence. So we wanted to involve some newer faculty and hear what they're doing. So with that, take it away, Fei.
Thanks, Aaron. Yeah, so great pleasure to be here today, and it was very exciting to see all the amazing talks and the platforms that presented in the previous talks. So my work focuses a little bit more on understanding the robot environment interaction, and specifically how can our robots take advantage of different terrain responses to achieve effective locomotion in complex natural environments. So this is one of our recent efforts in trying to send our electric machines to assist human geoscientists in a lot of scientific exploration missions. For example, Earth and planetary surface exploration and monitoring. So what's happening here is we are sending the Rex robot carrying a whole bunch of scientific instruments. For example, it can carry wind speed sensors and also can carry sortility sensor to see how many sand particles have been blown away by the wind. So as the robot walks around the desert, it can continuously collect all these valuable informations for human scientists. So help them to understand, for example, desertification and sediment transport process. However, in order for a robot to basically robustly operate in these different environments, there are still a few key challenges that we need to address. So one of the key challenges here is the natural substrates really comes in a wide variety of forms. So as you can see here, for example, the deformable substrates we can see in natural environments, including snow, sand, leaf litter, gravel. So all these different things can have very rich properties and responses. For example, upon the robot-like interaction, the sand can yield initially, but at a certain point can suddenly solidify. So it can exhibit the responses anywhere between solid-like and fluid-like. And these unexpected responses from the substrate can often lead to locomotor failures. So in my previous work, I take a robophysics approach to help to improve the mobilities by first creating simplified model terrains in laboratory environments. So we can systematically perform experiments to understand these substrate interactions and responses. For example, in order to emulate a wide variety of natural substrates, deformable substrates, such as sand and soil, we can basically blow air through sand particles in the lab environment to systematically control and vary sand stiffness. And this will allow us to start to perform granular physics experiments to analyze the force responses and also to understand the dominant parameters governing locomotor performance for both robots and also legged animals. And through these experiments, we can start to extract interaction models that's general enough that we can feed back to guide the design and control of robots when they operate in natural environments. For example, in our previous work, we have discovered that robots can actually take advantage of either solid-like responses of the sand by basically pushing their feet deep into the substrate slowly and exploit this hydrostatic-like force to generate enough support. Or if it's for small lightweight platforms, they can actually take advantage of fluid-like response of sand by slapping their feet rapidly enough on the surface and take advantage of the substrate inertia to generate a very large hydrodynamic-like force to achieve fast running. So with these different understandings, when we go back to bridge the gap between lab results to natural environments, one of the complexity is the natural environments. The soil properties or the substrate properties can vary significantly spatially, both horizontally and vertically because of different environmental controls. So one of our ongoing efforts is to take advantage of this excellent force transparency property of the direct drive actuators. So as you can see from the video, Turner was blowing air on one of the direct drive motors. It can sense these responses quite sensitively. So previously, we were basically building direct drive robots, robotic legs that using these direct drive motors, so they can basically sensitively feel and characterize the soil responses during each interaction. So we deployed these robotic legs as first not as locomotive appendages, but as novel soil sensors first to basically map out the soil erodibility and property across the desert fields. So we take the robotic leg to the desert and we perform different sensing activities. So one of the interesting here is basically it's not a one shot, it's not like taking one value. So depending on how the leg interacts with soil, it can actually gather different information about the environment. So either through different interaction angle or speed, it basically sends different responses from the terrain and can help to infer what environment controls is governing these properties and responses. So with these different understandings also helping us develop a knowledge base. So going forward, what we are trying to do is basically to build these multi-leg robots using direct sensors so they can rapidly walk around the desert and to assess the soil erodibility across the entire dune field and feed this information to either a teammate robot that carries more comprehensive sensors or to communicate with the human teammates. And these opportunities are also helping us understand how humans make or adapt their decisions in situ experiment plan in these scientific explorations. So we're currently in collaboration with cognitive scientists trying to understand how humans adapt their experiment plan in response to these dynamic incoming information provided by the robot, which was not available before. Another interesting challenge that we face is sand is complicated enough, but many natural environments not only include sand, but also contain larger terrain heterogeneities, such as rocks and bubbles. And these different terrain heterogeneities is going to pose large perturbations to our electric machines and making many of the existing methods developed for flat and rigid ground, such as the finding collision free path or static foot placement, cannot be directly applied. So we're really in need for additional methods trying to understand how to engage with these large heterogeneities in our terrains. So if we look at biological locomotors, humans and animals were not afraid of interactions and collisions. And on the contrary, many times we'll actively engage with obstacles. For example, we can push against a wall to turn faster, or we can basically push against obstacles to basically jump higher. So if we can rethink about obstacles not as something we need to avoid, but as interaction forces and opportunities that we can exploit, the question that we want to ask is, can we basically gather enough understanding so that allowing our electric robots or even other different platforms to understand how these different locomotion dynamics are governed by different contact modes, and so that our robots can basically intelligently start to select appropriate physical interaction to help them navigate these environments. So for a quadrupedal robot, it can basically perform different gaits. So here we are running the robot with a bounding gait, which is the front two legs move together, alternating with two back legs across an array of obstacles in front of it, cylindrical obstacles. And what we are seeing is with the bounding gait, without any body level steering, the robot always passively converges running perpendicular to the obstacles, 0 degree. Whereas if we do not change anything else, but only ask the robot to change its gait to a trotting gait, meaning the two diagonal legs move together and alternating with the other two legs. Again, without any body level steering, the robot will passively converge to positive or negative 30 degrees, depending on its initial condition, very robustly. So why is this interesting? It's because bounding and trotting are only two different gaits out of infinite gaits within a three-dimensional space. And if we basically, if we can understand this steady state orientations, how it's governed by the obstacles, so we know that the trotting gait will automatically have a lowest energy point, meaning a steady state at 30 degrees. So anything around that initial orientation angle, the robot will basically be converging to 30-degree orientation. However, if for a different gait, for example, bounding, it has the lowest energy points or steady state at 0 degree, and attracting pace includes this 30 degree, then if the robot suddenly switch to a bounding gait, then it'll start to follow this red line and start to converge to 0 degree. So we have unlimited gaits in our gait space a quadrupedal robot can perform. So if we can understand and predict these steady states and their associated basins, we can start to compose these obstacle modulated steady state to allow the robot to exploit its shape of its environment to robustly navigate itself. For example, we can basically first perform a trotting gait, and we know that let's say it takes anything between 0 to 50 degrees and allow the robot to always converge to 30 degrees. If we compose with bounding gait sequentially, then we can basically take anything between negative 40 to 40 and convert to 0 degree. And by keep doing so, we can just by switching through different gates, and instead of fighting against our environmental obstacles to steer ourselves, we can allow the environment to basically take us to the desired trajectory that we want to go. However, what this requires is for us to have a good understanding and prediction of where these steady states lies and what's the mechanism for these attracting basins. So in our recent work, what we're trying to do is trying to create a representation and a framework that allows us to generate, understand these steady state behavior. So for example, in our previous work, we discovered that the obstacle disturbance force on the robot leg is primarily determined by the 4F contact position on the obstacle. So with that, we can actually convert or represent our 3-dimensional environment with a 2-dimensional disturbance force field. So depending on each different contact position of the leg, we can basically map to a corresponding obstacle disturbance force. And by adjusting the different contact position on the obstacle, a robot can manipulate these different disturbance force to generate desired dynamics. And in addition, for multi-leg robots, at any certain point, they can choose which leg to engage with the available disturbance or not. So by specifying a certain gait, it's basically specifying the activation pattern. For example, the bounding gait, the 2 front legs have to select the obstacle disturbance, whatever is available at the same time, and alternating the other 2 legs. Just by subscribing these different activation patterns, we can see that we will have different resulting dynamics when we push the robot through the obstacle field. So disturbance selection framework allows the robot to use different gait to generate different dynamics from even the same physical environment. So just with this very simple representation, we can see that when we basically put the robot subject it to the different obstacle disturbance force in the same environment, with the bounding gait activation pattern, the robot will converge to 0 degree, and the trotting gait will converge to positive and negative 30 degree. So the model will also allow us to start to generate analytical prediction of where the steady state orientation will lie and how that basically will depend on different parameters. For example, the robot aspect ratio, the obstacle spacing density, as well as different gaits. So here's some preliminary results. We're trying to see just by moving through different gaits, we're trying to have the robot, so without any body level steering, just let the obstacle take the robot to the desired trajectory. So here we have some initial preliminary data to show that basically the robot can actually take advantage of the obstacle disturbances to achieve the desired trajectory very robustly without active steering. So with that, I would like to thank you all and see if there's any questions. Thanks.
Great, thank you for the talk. Very, very interesting seeing the interaction between the robots and the world as being the driving factor. I think that's largely underappreciated. In the first part of the talk, you had this phrase, which I liked, which was every step is an opportunity, talking about locomoting and granular media specifically. Could you give some more details about the models you used for granular media in that case, the different terrain types, and how you imagine learning those models? And I don't mean necessarily learning per se, but ways of using data-driven approaches to characterizing the models.
Right. So yeah, thanks for the great question. So basically, what we are trying to do is really understanding what's the dominant parameters that's determining the twin responses and basically the resulting locomotor performance. So for example, we found that there are different regions and different parameter sets that will basically generate the granular twin responses. For example, if we push something slowly into the sand, you basically will get a linearly increasing force with the penetration depth. So it's almost like hydrostatic-like, versus if you have a high impact speed on the surface of the granular material, you will actually have a quadratic dependence of the force depending on the speed. So those responses are sensibly related to what locomotion strategies might be effective for different locomotion modes. However, in the natural environment, so why we need this direction of sensing is because the soil can basically, property can be governed by a mixture of different environmental controls. So for example, it can be a composition of different soil stiffness in both vertically and also in horizontally. So one of the things we are trying to do is basically using the knowledge we gather from granular force experiment to help us interpret the soil responses. So from every interaction, we are trying to see what response we get for under a certain sensing protocol, the lag action, and then help us to infer maybe some of the gradient in the environment. Maybe the sand is getting softer and softer towards a certain direction, or maybe there are certain repeated environmental controls. Let's say moisture is periodic, let's say every sand dunes. So with those informations, the robot can start to have a different kind of horizon of predictions on how the environment property might be changing, and also to help it to adapt its both sensing protocol as well as the locomotion strategies across these terrains.
Great, great answer. This is it's a very fascinating field. This granular media intrusion models, very cool. Any questions from the audience? Someone asked, can you comment on how to extend this to locomoting through non-uniformly spaced pipes?
Yeah, so that's a great question. So one thing that we are trying to do is, let me see if I have the slides here. We are trying to basically, again, applying the direct drive. So we are looking at this in two different ways. So one way is basically we are trying to relate this to biological studies. So we have been running some experiments on how animals adapt their gaits through different obstacle fields. And also we're trying to learn some of these reactive strategies. So basically how the leg face will adjust upon the disturbance. So there have been some preliminary results understanding upon leg perturbation how animals adjust their gaits. So one of the things we're trying to do is based on our previous model, we're trying to generate a derivative graph. So basically takes one robot state to the next, depending on which group of leg we can actually activate. So that will basically be less dependent on the uniform distribution of the obstacles, rather than say, okay, here are the environment prediction on interaction force distribution. And at each step, depending on what's the goal of the locomotion, let's say you want to turn as fast as possible clockwise, then which of the leg you want to engage with the obstacles to generate the force towards that direction. So that was also another direction we're looking at. So both directions will hopefully take us to having the robot maximally taking advantage of its environment to reach desired response and dynamics.
Great, great, thank you.
Thank you.
All right, I think we'll jump to the next speaker now for the sake of time.